Okay, let's look at the second shuffle, the top row, but the one on the right. The only difference here, if you contrast it with what we just did, the stacking will be the same, involving this leapfrog technique, but we will then stack the right pile on top of the left. Okay, so that's the only difference. And the claim is the cycle notation for this permutation is the following. Parentheses 1, 6, and then a set of parentheses 3, 8. Okay, so let's just quickly step through this. Okay, so you just start with 1 through 8, as we have. Perform the shuffle itself. So we're dealing into 4 piles. We're going to do the leapfrog. So 1 goes and gets stacked on top of 3. 2 jumps over 3 and gets stacked on top of 4. Now we stack the right pile on top of the left. Okay? And as you might imagine, that's going to change the order of the cards from what it was in the first example today. Okay, so this is what we get. We get 6, 2, 8, 4, 5, 1, 7, 3. Okay, so that is how I got Cauchy's two-line notation for this permutation. That bottom row right there is 6, 2, 8, 4, 5, 1, 7, 3. And we can change or convert this to cycle notation, which is far more compact. So what we do here is you just look at 1 on the top row. Where does 1 go? 1 gets sent to 6. So 1 goes to 6. 6 goes to 1. So it wraps around. So we get this little 2 cycle, also called a transposition. So 1 and 6 just switch places. Now 2 goes to 2, so it's a fixed point. 3 goes to 8, and 8 goes to 3, and then it wraps around, so we get a second transposition, or 2 cycle. And then from there, we just get a bunch of fixed points. 4 goes to 4, 5 goes to 5, 7 goes to 7, okay? So if we color code all of this, what we'll get is the following. Remember, 1, 4, 6, 7 are black. 2, 3, 5, 8 are red. So we will not have, quote, inversion this time. So black 1 goes to black 6, and then black 6 goes to black 1. Red 3 goes to red 8, and then that gets sent to red 3 again. Now, red 2 stays where it is. It gets sent to itself. Black 4 gets sent to itself, red 5 gets sent to itself, and black 7 gets sent to itself, okay? Now, we've mentioned this before. Normally, we do not write single cycles or 1 cycles when we're representing a permutation using cycle notation. As long as we know the size of the set we're working with, we can actually drop these little 1 cycles. They are also called fixed points because that's what they do. Whatever's in position 2 gets returned to position 2. Okay, and same thing for position 4, 5, and 7. So here, each value gets sent to a value of the same color. So there's no inversion here. Going back to our sets here, what we're saying is these position values, or the objects in these positions, will be sent to these same position values, even though they might get reassigned within that set of values. The same thing here for a complement. The objects in positions 2, 3, 5, 8 will stay somewhere in positions 2, 3, 5, 8. Okay? So there's no inversion. Inversion happens when this occurs. So it's exactly preserved. Now, what that will mean for our Bessey sequence, and I think you can probably begin to anticipate this now with all of the practicing that we've been doing, is if we start with our the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, and we perform this shuffle, what will happen is we will get that same form back. It won't be inverted. Okay, so we do this leapfrog. 1 gets stacked on top of 3, 2 gets stacked on top of 4, and then it's right on left. So we will get back to 1, 0, 0, 1, move that over, 0, 1, 1, 0. Okay? Now, it is true that some of these cards, some of the ones have moved around among themselves, and some have stayed fixed, and some of the zeros have moved around among themselves, and some have stayed fixed. So this is what the shuffle diagram would look like for shuffle 6. And as pointed out up here, inversion does not occur.